Alrighty, so today we're going to walk through a force balance, a statics problem, and resolve the forces and determine any unknown forces. So here you see that we have a force here acting along the beam, and we're also told that the beam at point A is pinned down, so it acts like a pin at point A. So, and then as well, the mass of this beam here is 800 kilograms. So the first thing that we want to do is draw our free body diagram. And so what we will have, is something like this, where I draw the beam. We'll have a force acting in this direction along here. We'll also have a force due to gravity, the weight of the beam there at the center of gravity. Where we also have a distributed load here, a triangularly distributed load here. And then as well on the other side, we have another triangularly distributed load. And then like we were told before, at point A, it acts like a pin. So we have AY and AX because the reaction forces at a pin are in the horizontal and vertical directions. So we also have some dimensions. So this distance here is 4 meters. This distance here up until the force F is 6 meters. And then this distance at the top of the beam to here is 0.5 meters. Okay, so the first thing we should probably do is find the resultant load from these two distributed loads. So in order to do that, we were given the load per meter, right? Here, let me underline it here and here for both distributed loads. So we'll do the right side. So what we need to do is just take 310 kilonewtons. Sorry, let me rewrite that. Kilonewtons per meter. Multiply that by the distance or by the length that the load is distributed across, which is 6.5 meters times 1/2. And that's the 1/2 just comes from the fact that it's a triangularly distributed load. So we solve for that and we get 1007.5 kilonewtons. Next, we'll do the other side and we do 118 kilonewtons per meter multiplied by the length of the distributed load, which is 4 meters multiplied by 1/2. And then that comes out to be 236 kilonewtons. Afterwards, we can resolve the weight force, which is just going to be 800 kilograms times 9.81 meters. And in that case, it is 7.848 kilonewtons. Okay, so now we have now we need to find what AX is, AY is, and F. Oh, and actually one more thing. We need to, now that we've found these two distributed resultant forces here, we need to find out where they act along the beam. So in order to do that, when it comes to triangularly distributed loads, we just multiply the total distance by 1/3 from the side with the greatest force. So in our particular case, we just take 1/3, multiply it by the total length that the load acts on, which is 6.5 meters. And that comes out to be 2.167 meters from the bottom, because the greatest force is right here. So that would mean that the force resultant acts somewhere along here, and that this distance is 2.167. And we do the same thing for the other side. So 1/3 times 4 meters, which is just equal to 1.33 meters. And so that acts right there, 1.33 meters. Okay. So next, what we want to do, the easiest thing to do, because we have three unknowns, the quickest way to solve this problem is to take a moment balance at point A. And then because this is a static problem, it's not, there's no moving pieces. This is all going to be equal to 0. And so what happens is these two forces are canceled out due to taking the moment at that support. And then so what we're left with is just 0 is equal to, we need to take the resultant forces that we found. So we have 1,000, 1,007.5 kilonewtons multiplied by the distance from point A, which is 2.16 meters. Next, we have, and in this particular case, this value is positive because we're going in the counterclockwise direction. And then the clockwise direction, because you can kind of imagine here, so if this force acts in this direction, it's going to rotate this beam at point A like so. And so that gives us a counterclockwise direction. And then similarly for clockwise, if we rotate the other way, this system is considered clockwise would be considered negative, and then counterclockwise is considered positive. So next what we'll do is subtract the other side, which is 236 kilonewtons multiplied by the distance, which is 1.33 meters. And then we also have to include the this unknown force up here, F. So again, this will rotate from, if we take F and sort of pull it to the right, it'll rotate about point A in a clockwise direction. So then we get negative F. And then we got to multiply it by the distance that it is from point A, which is just 6 meters. So what we can do is rearrange and solve for F, which would give us 311.44 kilonewtons. So now we found F. And next, all we need to do is find AX and AY. So that what we can do for that is just take a summation statement in the X direction for the forces in the X direction. Once again, that's all equal to 0 because it's a static system. So we say we have AX plus 236 kilonewtons minus 1007.5 kilonewtons. And so once again, we solve for X or AX, and in our particular case, that would be 460.1 kilonewtons. All right, last step here. So now we need to solve for the AY. So once again, summation statement for forces in the Y direction. So this is 0, which is equal to AY. And then we have this force right here. The weight of the actual beam. And so earlier we found that to be, minus 7.848 kilonewtons. Once again, just rearrange AY, which that just equals to 7.848 kilonewtons. So here we have all our forces. We have our F force, we have our AX force, and then we have our AY force. And that's it.